Up next, we have our general purpose robotics panel with Dr. Peter Stone moderating. On the panel, we have Dr. David Fridovich Keil and Dr. Roberto Martín-Martín. Please join me in welcoming them.
Great. So to kick off this this discussion, and I want this to be as much a discussion as possible. So we can talk here for a while, but as one of my colleagues said, the job of a professor is to profess. So we can sit up here and profess, but I'd much rather converse. So we'll have plenty of time for Q&A at the end. But also, if there's something we say and you want to interject, raise your hand, and we can make this very much a conversation. So. So first, I'll briefly introduce the panelists. So David Fridovich Keil is a professor in the aerospace engineering department. Did his PhD at Berkeley. Works in autonomy, control, multi-agent systems, dynamic game theory. And then we have Roberto Martín-Martín, who did his PhD in Oliver Brock's lab in Germany, and then his postdoc at Stanford with Fei-Fei Li and Silvio Cervese, and works in mobile manipulation, robot learning, and both working towards this theme of general purpose robotics. And so. This panel will be very much teed up by Rodney's keynote. We're not going to be talking about products today. These are not, we're not going to be talking about markets. We're going to be talking about what are the core technologies that we need to be working on towards sort of unlocking future capabilities that may, after 10 or 30 years, get into products. And so just to read out loud the description, it says, the topic is, in recent years, we've seen remarkable advances in intelligent robotics driven by breakthroughs in AI and robotic hardware. However, and this is that Rodney emphasized very well, achieving safe and reliable general purpose robot autonomy in human-centered environments remains a significant challenge. We're not there yet. So the questions we're going to address are: what are the major technical gaps? What research problems hold the key to unlocking the next generation of generally capable robots? And during the discussion, we'll discuss the key challenges and share how their research is aiming to shape that. But before I do that, I do want to Rodney also mentioned RoboCup. And RoboCup is this initiative that I've been a part of for many years, and it was started with the goal of using soccer as the test bed, but there also is a component of RoboCup called RoboCup at Home, which is very much about general purpose service robots or general purpose robotics. And so I'm just going to give you a little bit of a video of what these competitions look like. As a way of motivating, this is very much in an artificial situation, so we would not call this real world. This is not ready for product at all. But it's a challenge where robots need to be put into sort of a 4-room mock apartment. And then they are given a command that they haven't been told before ahead of time what they're going to be told. They're given it in natural language, and they have to try to execute it. So this is a video from the most recent RoboCup at Home competition, which happened in Eindhoven last summer. So again, this command wasn't told in advance. It's all through natural language. There's no, no sort of secretly typing. And now it's going and finding the gesture of the person in the kitchen, and then driving towards the person. It knows where the shelf is. It has a map of the environment beforehand, and we'll see if it completes the task. So that was a complete, and it's a 5-minute task. So if it completes one command, then it has to drive back to the starting place and then receive its next task. And now, of course, the robot could go and pick up all the objects on the kitchen cabinet, or it can look at the objects and make a guess at how heavy they are. And so this is sort of the setup. And just to give you the sort of the range of kinds of tasks that the robot needs to do, here's just a very short video of the kinds of things it needs to do. So there's like a party host task, there's a set the table task, there's putting away groceries tasks, but those are all sort of known ahead of time. It's this general purpose service robot task where it has to take the command from a constrained language, but very large language, and so that it can't have practiced all the tasks ahead of time, and it needs to go and try to accomplish those. So so this is just to motivate what the dream of general purpose robotics would be, or general purpose service robots. And obviously, we're far from that. That's not at all towards a product, but it is sort of illustrating what some of the challenges are. So to kick off this discussion, maybe let me give each of you some time just to say, what inspires you about general purpose robots? What's the research that you're doing that's most related? And what do you think of are the biggest and most exciting challenges? Maybe Roberto, go ahead.
Okay. Hello. All right. Yeah, thank you, Peter. Hi, everyone. So, yeah, general purpose robots. Okay, gone away. Yeah, my research is very much related to that, and I think one of the good things that we have seen in recent years is this idea of having some non-zero generalist policy. So we have seen here some examples from Peter, possibly a little bit curated. There are possibly failures even in this very simple task. So I'm very interested on that part. What happens when the robot fails? How can it fail in a more graceful way? How can it recover from those failures? And when it fails, how can we make it that is not catastrophical? That is something that I'm very, very excited about because I believe maybe in the future there is some way to make perfect robots that come to your house, you press a button, and they are amazing everywhere in everything that you want them to do. I don't think we're there yet. I don't know if we're going to get there ever. I don't think even for humans that is something, you improve on your job, right? So what I want is to be able to bring a robot that starts to do something, that it does it and learns from its own mistakes, and the mistakes that it does are not catastrophic for itself or for the environment. And I take a lot of inspiration from the best example we have, which is humans, I would say. So there are several things that can be learned from humans. One that I find very interesting, we have some kind of like universal ways of avoiding catastrophic failures, if you can think of it. Just think of pain as a universal nature form to kind of like avoid that you do something really bad for yourself. So I'm interested in thinking, are there some universal catastrophic errors, preventers, or kind of like avoiders that we can embed into our robots that allows them to learn in a more safer manner for several tasks instead of just doing specific safety for each task individually. And the other thing that I like about humans is our embodiments are also quite well adapted to be safe, in a sense of, if you see babies playing around, they can hurt themselves, but usually, I mean, they kind of like adapt themselves, they kind of like touch things in a way that they don't break. If I try to do that with one of my robots and they kind of like blindly try to grasp something, they're gonna break. So the other thing that we explore is how can we combine algorithms with intelligent embodiments so that they can explore in a safer manner without breaking themselves. And that includes, different embodiments and sensors, for example, tactile information, force information, that it allows the robot to explore without damaging itself or the environment. So yeah, these are just two things that I'm interested about on how to really go from a generalist, non-perfect robot into something that is better for the environment in a safer manner.
Great. So graceful failures and being able to learn learn in a safe way. Those are things we can definitely dig into. But before we do, maybe let me turn it over to you, David.
Yeah, those are great, very interesting points. I'm also interested in some of those as well. I guess maybe the main point that I also work on that maybe hasn't been mentioned yet is I'm very interested in how robots can interact with people or even other robots whose intentions maybe they don't exactly know. So that's comes up all the time. I was exposed to this problem first. I interned at a self-driving car company in graduate school, and there were all kinds of complicated problems that people at the company worked on: perception, prediction, planning, control, up and down the stack. And there were all kinds of problems that we'd hit. Every week there'd be bug reports coming from all these areas. But the ones that were the most consistently pervasive, problematic for the company, and I think pointed me in the direction I've been going since then, has been like at the intersection of predicting what is going to happen in the future and planning in response to that prediction. And so that shows up all over the place. It shows up certainly in navigating through busy intersections, merging onto traffic, busy highways, but also in these sort of home robotics scenarios. So I started interacting with those problems midway through graduate school and started developing kind of a game theoretic perspective on all those problems. So I guess that's maybe the angle that I've had on what are the hard, interesting problems in robotics for the last, 8 years or so. And it keeps being a source of exciting stuff.
Great, and just so the audience knows, we didn't rehearse this at all. So this is we're going to we're surprising ourselves where we're going as well. So there's some great things to dig in here, though. I think I'll summarize what you said, maybe, David, as some of the challenges as being dealing with the unknown unknowns, the things you couldn't predict ahead of time, and maybe also connecting with Rod's talk, this notion of having an internal simulator, of being able to sort of model internally what's going to happen in the world and use that to predict and plan, which is not really there in the end-to-end kind of paradigm right now. Is that a good summary?
Yeah, I think that's very fair. I think the particular element that I'm sort of poking at is sort of where that uncertainty comes from, the sort of reactions of other decision makers, right? So in the home robotic settings, people interacting with the robot, right?
Yeah, so let me maybe riff a little bit on this sort of graceful failures and the unknown unknowns aspect. And this isn't about autonomous cars. This is about general purpose robots. But I've been motivated in some of my research by I think Waymo at one point put out to motivate this unknown unknowns idea. They I think had a blog post at one point where they said they try to predict everything that might happen, but one time their car drove around the corner and there was a woman in a wheelchair chasing a turkey with a broom, right? And that was not something they had simulated. That was not something they had foreseen. And you would sort of expect that when that happens, the car's not going to respond the right way the first time. But you'd want it to fail if it's going to fail gracefully, not to maybe to stop, maybe to be confused, not to run over either the woman or the turkey, and maybe to back away and try a different road or something like that. But you'd also like that it never makes that same mistake again, right? That if it ever turns the corner and sees that same situation or a similar situation, that now the next time it will be prepared. And I think you say kids or humans have this idea of avoiding catastrophic failures, or at least learning quickly from them, right? If a kid touches a hot stove, if there's a hot stove, maybe the kid will touch it once, but not twice, right? And so I guess this.
I'm not sure, but in Spanish we say humans are the only animals that that kind of like stomp on the same stone twice.
Yeah. So maybe not all humans. But I guess this gets me to the question sort of what is the right model for understanding when a robot is ready to deploy? Is it the provable guarantees? Is it the empirical, we've tested it enough? Is it that it'll never have any failures, or is it that it knows how to gracefully fail and then never repeat the same failures? What should be the standard that we're striving for before we're ready to get those the robots? And what's the research that this motivates?
Want to take on that?
Yeah, I mean, I can start. So with the caveat that although I'm in an aerospace department, I've never worked for a major aerospace company. I've been very aware that the aerospace sector has got a very nice, except for recent months, track record in safety, right? So the verification validation pipeline, you can go and look up FAA V&V on Google Images, and you'll see a V shape where there's kind of a clear set of steps that basically go through the companies have to go through to convince the FAA, hey, my product is safe. And both verify it. That involves some theory, some basically arguments that, hey, the design is sound, and then also some actual experiments that basically test, hey, at different parts of the flight envelope, the controllers are good, as an example. So with the, again, caveat that recent months have maybe seen some more aerospace accidents than we would like, I think that is something of a gold standard. I don't know if it's the right gold standard. So progress is very slow. You see the pace at which new aircraft come out is quite slow compared to new cars, for example, new robots. So I don't think it's the right standard necessarily, but I think it does give us something to shoot for in terms of there being a clear regulatory environment for, basically for processing new products. So that's.
But I mean, I'll just point out that, on the other hand, that when a human drives or flies a plane, we don't have any provable guaranttees about them, right, or their brains, right, 100%. And yet we trust the human pilot, and so
100%.
So I often wonder about the opportunity cost of that we have from provable guarantees that might sort of stop us from doing things that are good enough or useful or better than people. So
actually, so to be clear, I 100% agree with you, and actually, a great point here. When they make a new airplane, my understanding is they basically freeze the chipset, that all the chips that are running in all the flight controllers in the airplane. So Boeing comes out with 737 MAX. They go and buy a bunch of chips from, let's say, Intel. They put those in dry ice, liquid nitrogen something, and keep those for every future airplane they're going to build in that line. That's a huge limitation, right? That means new compute hardware comes out, we can't upgrade. So, I don't think as roboticists we would want to be committing ourselves to that. All kinds of other issues in terms of being tied to real-time software and that kind of stuff. But I guess the point being, I think there are huge limitations to going the kind of gold standard FAA V&V route, but it is maybe an upper bound.
Yeah. So Roberto, maybe this comes back to you. So you said that.
I wanted to add to something that David
please.
said, and to this kind of topic. I think it's about, we are a little bit of control freaks, and we think we are kind of a bit more calm if we think we understand what's going on. I think it's first is some form of fallacy, and you mentioned very quickly, unfortunate accidents are happening, and that's true. And I think that this part of the Boeing that went out, do we even know why it happened? I don't think we end up knowing. The systems are so complex that even the ones that we know how it works for small parts, okay, the chip, we know how it works. This wheel, we know how it works. With the motor, we know how it works. You put everything in combination, and it becomes very, very difficult. But we still have the feeling we understand better than if it's a big neural network. So at the end, I think, if you are going into that, if the gold standard is to make some tests and get some probabilistic proofs of, okay, errors are going to be less than 0.01 in these conditions, and that is empirical, I agree that this is a good standard that I think we can also bring into robotics and into even machine learning. But if it's under the assumption of we need to understand how each output is generated, we are not going to be able to do it with the models that we're going towards in AI. And I don't think we're able to do it also with the big complex machines that we're currently doing, but we have the feeling that we do. So that is what I think is the small fallacy in terms of controllability or understandability.
Yeah, maybe like another way to put that, to which I'm, again, just basically agreeing with you in different words, would be, so even, I think if we accept that the world is complicated, models are wrong, and anything we would ever say is only going to be true in a certain set of circumstances, the flip side of that would be to say, look, if we can't even find a set of circumstances in which the thing we're doing is correct, that's probably bad. So I think there is that kind of flip side to the argument, and I think that's maybe the camp I fall into a little bit more. You know, another sort of flip side to this would be to say, look, there's always uncertainty. Maybe the best we can do is make some very high probability guarantees that things are going to happen. Okay, fine. But the problem is, the higher the confidence level you want to achieve, kind of the harder that is, because in practice, the noise in even sensor measurements and things is going to have a good chance of washing out any guarantee you're making. So it's a hard problem. All these things are very hard. But my general, I don't know, philosophy on it would be, I'm going to accept that nothing I do, no guarantee I make, I write in a paper is ever going to apply to a real physical system that isn't exactly what I modeled. On the other hand, if I can't even argue that the thing I'm doing is correct in a simplified setting, it's very hard for me to trust it.
So let me pull us back a little bit towards general purpose robots, because when we're, you know, if an airplane, if there's an error, it's going to be catastrophic. But Roberto, you made a great point that you know, babies, when they learn, are doing it in a sort of, you know, relatively safe environment. And reminds me of, like, you know, when you see little kids learning to ski, right? They're fearless, because if they fall, it's not going to hurt. They're close to the ground already. And adults learning to ski for the first time, it's much more catastrophic. So there's this sort of situation that we, you know, sort of learn in a growing body and in more and more dangerous, you know, and we also engineer that for babies. We put them in sort of a playpen first. So what can we leverage from general purpose robots, this dream of having robots in our home, that's a sort of a less high stakes setting, that could sort of riff on that or build on that, and you know, how can we, you know, how does that motivate, again, sort of research directions and opportunities?
I mean, definitely we can learn from errors. It's not as catastrophic as you mentioned with a plane. I mean, still, for my lab, if the robot breaks, it's quite catastrophic. So I try to avoid it. And I also think it comes into the future. I think here my idea is not... So what I assume is that you need a robot that can learn from its own mistakes, even on the job, even when it's deployed. So then it goes into something that you say we don't want to talk, which is more of the commercial aspect of it. You don't want a robot that is breaking all your, I don't know, all your plates in order to learn how to put plates in a dishwasher. So it should be efficient, as you mentioned, and be not as catastrophic. Even for that, you don't care about one plate, but you are not going to purchase that robot. So there is a balance in there. We have a lower bar in terms of, okay, the errors are not as catastrophic, many of them, but still the bar is high if we want to provide a solution that is actually something that people want to use. Mm-hmm. We don't have that in the lab, that's true, but still in the lab we have the other constraints of, okay, I have 2 robots in my lab. If one breaks, then that's catastrophic for my lab. Yeah. So still we have kind of like some bar of efficiency and kind of like graceful failures that we need to achieve. But I'm looking more on a solution that for general purpose robots that people would like to have in their homes. So it needs to be able to fail gracefully and hopefully not catastrophic and still learn from that.
Yeah, so maybe let's talk a little bit about what's the right type of learning or the locus of learning for a general purpose robot. So our colleague Leslie Cabling at MIT often gives talks about this. You want your robot to learn how to cut vegetables, but not in my kitchen, right? I want it to know how to do it by the time it gets to my kitchen. And so, often we think for general purpose robots, there's the time when they're being developed in the factory in a very, when they don't yet know anything about your kitchen and they're learning the general skills, or being programmed with the general skills, where there's the opportunity maybe for lots of data. But then when they come into your home, you want them to personalize to your home quickly and safely. And so there needs to be, there's opportunities for learning at both. It's sort of both in the factory and in the end user's home. But how does that learning differ? And what how do you see that they relate to each other? What are the different methods? Either of you.
Sure. Yeah. So I guess maybe this relates to what you just asked as well as the sort of previous topic. But something several of my students are getting interested in is like basically how can you use a imperfect model, but still a model of what's going to happen, right? In order to align the sort of behavior you learn from that model to just a few examples. It's essentially this question that you're getting at, and this is a topic many people have worked on for years. But I do think that there's some interesting ground here. So, for example, one interesting fact that we've been able to show is that if you have some process, some sort of ability to kind of control the error between the two so that they never diverge, right? So the predictions of your model, basically, sure, they're going to be wrong, but as long as you can make sure that they are never kind of wildly diverging from what actually really happens, with some mathematical details, that's enough to guarantee that the thing you learn on the model is actually, basically the thing you learn from the model is going to do well in reality. There's some caveats, but I guess the point being, I think there are some fresh perspectives to be had in terms of leveraging approximate, error-prone, but maybe analytical models. Analytical models, we have access to things like derivative information. Many people here will be all very familiar with differentiable robotics, differentiable programming, right? So models that give us access to those tools that we can use to design controllers, design high-level policies even. There's fresh perspective to be had in using those models for deploying on the real world.
Good, yeah, and maybe Roberto, like if you're thinking on this, like, if we're going to have the robots in the factory and then in the home, what aspects of this development cycle are right for control theory versus reinforcement learning versus learning from imitation or demonstration or other methods? And how do you combine them?
Yeah, I think there are two aspects of it. The first one is this idea of, can you learn some initial policy or behavior? Let's call it behavior, not policy. Can the robot generate some initial behavior that is not too bad to start with? So I think that is going to be critical for general purpose robots, and that is the part that you want to learn in the factory. Then you want to adapt it to your preferences, to your own house. For that, one of the things that we are exploring is kind of like elevating the question, so can we embed robots with the capabilities to learn, for example, from humans on how to perform those tasks in a better way. So that is imitation learning in this case that we use in my lab. And we connect to the previous topic and try to make it safe so that the robot tries to look what the human is doing, imitate it, but imitate it in a safe manner, and then learn to adapt from some initial set of capabilities. So that is what we're trying in my lab, and I think that is a good recipe. So giving up on having the perfect robot, so like you say, there is part that is going to be in the factory, there is part that is going to be on the job. So have some initial set of capabilities that is a good starting point, that the robot doesn't have to randomly explore with a knife, going around to try to learn to cut vegetables. But still, if it's a new knife, it may need to kind of like look at me doing it or explore on its own. That will be more kind of like some reinforcement learning or other type of formalism. Still, these two processes I would like to be safe. And for that, having some model of some predictive model in any form, explicit or implicit. You were talking about predicting if a woman is going to be there with a turkey. That is very explicit, but predicting if something could be around the corner is maybe less explicit, but still helpful to say, okay, let me brake. And that's actually, I think, what I do. I don't know if something is going to be there, but I predict that something could be there. So this type of more intuitive models can be very helpful and very powerful for a robot that is supposed to be generalist and doesn't know what exactly is going to be encountering.
Yeah, and maybe this is, David, this is getting what Roberto's talking about is learning from demonstration, is getting us towards something you think a lot about and is also dear to my heart, is sort of the multi-agent systems aspects of robotics. And so, learning from, in this case, if there's a person and a robot, this is two different agents. The robot's not in a vacuum, but can learn from watching you, maybe also learning from feedback, right? You don't necessarily need to demonstrate, but you could just say, do it more like this, or good job or bad job, or, so there's different, or maybe even interventions. Let me take control for a little bit and then I'll give it back to you. So there's different interaction modalities with people, and then we might also, in a general purpose setting, have multiple robots in the same in the same environment. So David, you want to comment anything about that? What that opens up?
Yeah, sure. Yeah. So what that actually makes me think of is a problem I first encountered when I bought a new car a few years ago, and my previous car was like 25 years old, and this new one came with a lane tracing assistance. So it's what I initially thought is, okay, this thing is basically trying to help me steer the car, but it's trying to figure out, like, am I being intentional about the way I'm steering, or am I distracted? Right, that's kind of the question it has to face. And so there's some autonomy, there's a human being, me. I guess there's other cars on the road that maybe my car is not smart enough to detect, but a Tesla could. And so what's the interplay between all of these decision makers? Because I work on game theory a lot, my initial thought was, okay, this is a question where basically there's a human driver that sometimes, if I'm paying close attention to the road, I know what I'm doing. I don't want the autonomy involved. It's going to beep at me at stupid times, and I'm going to turn it off. But when I'm distracted, when I'm talking to a passenger, when it's late at night, I'm driving home from the airport, I may get distracted. And it'd be great if the autonomy could figure out, when am I kind of being a bit more passive, and when does it need to step up? And so there's a natural way to kind of frame this in terms of like a leader-follower interaction, where the hierarchy is not certain. The hierarchy can change over time depending on the circumstances, depending on who I'm talking to, whatever. So I guess this is a bit of a sort of a nuanced, specific example that's kind of you've made me think of. But I guess the maybe higher level bit to draw out of the example is that I think the interplay between human decision makers and autonomous decision makers, or even multiple autonomous decision makers, is one where there can be very complicated relationships between the decision makers, between the agents, and they don't always want the same thing, right? Different drivers in traffic don't always want the same thing. And so if we don't account for how one agent's decision will influence others in the future, that's sort of missing a big piece of the puzzle.
Yeah, and you're basically, the word sometimes people use for this setting is mixed initiative, that
Sure.
Either the person's taking the initiative or the robot's taking the initiative. It again makes contact with Rod's talk, where he showed the robots at the beginning where they can be autonomous, or a person can take over and say, now I'm in control. And this seems like it's very useful for a concept for the household or general robot autonomy as well. Maybe before opening it up for questions, maybe one more, we've been very broad ranging here, so there's lots of fodder for people to ask about. But Roberto, there is a lot of research now on robot manipulation, but often with sort of arms bolted to a table. And then there's been a lot of research on robot navigation with for autonomous cars, or in the household. Maybe again, Rod picked off perhaps the best application that requires no manipulation but just navigation, which was vacuuming. But most beyond that, most applications in a home are going to require some manipulation. So what gets what are the challenges when you take the arm off of the bolt, not being bolted to the table, but now being on a mobile platform? What are the opportunities it opens up, and what are the new challenges that arise in mobile manipulation?
Yeah, there's definitely that's definitely a game changer. So I think that we have to distinguish between the properties that we create when we have a stationary arm, possibly in the lab, for example. So what we need to do is that everything that the robot needs to have is kind of like over there. So we have to make the problem feasible. When we tackle mobile manipulation, then the robot has to explore and find a way to, basically the workspace is everything. There is a level of uncertainty that is higher, but there are a lot of opportunities because the robot can choose its own part of the workspace to interact with. Where do I put my base in order to kind of like manipulate? So yeah, there is definitely a lot of challenges in there. There is a lot of opportunities. One thing that I don't have an answer about, but it kind of like comes to my mind often is how artificial this is, in a sense. If you think about biological agents, we don't think separately so much about manipulation and navigation. It's more like a construct. I don't know if that is a good or a bad thing. I just sometimes think when you learn, when animals learn, when my dog learns, it doesn't learn, okay, now I'm going to move my legs to move myself, now I'm going to move my mouth to pick up wherever is on the floor. It's all one from the very beginning. Would it be better that we kind of like break those boundaries, those artificial boundaries, and try to always kind of like have one single behavior? Even in the vacuum cleaning, you say it's not manipulating. It's manipulating in some way, right? It's even an autonomous car is manipulating the people that are inside. So I don't know how we are defining those boundaries, but my open question is it good that we have those boundaries in a first step, or are we kind of like creating those boundaries and trying to solve the limitations that we are creating ourselves?
Yeah. Yeah, and I think at CES this year there was a vacuum cleaner shown with an arm on it to pick up things that were in its way. So that's putting them together. So we've been very broad-ranging here, talking about sort of graceful failures and unknown unknowns and internal simulators and learning while you're small and mixed initiative and multi-agents and mobile manipulation. Hopefully this is the main. Hopefully this has opened up a lot of questions. And so let's move to the phase where discussion or comments or questions from all of you. There's in the back there, and then coming to Rod. Go.
Thank you. I wanted to ask, do you see there would be any universal standard that would define the rate of failure that is acceptable for a robotic system? And I was hoping to see a future that at least in the Austin robotics ecosystem, we would have that standard defined. Well, that's the ideal world.
One of you want to answer? What's the acceptable level of failure for a robotic system?
I guess it depends on the application. And I like something that Peter says, that we're becoming kind of like robot psychologists in a sense, because we're kind of like analyzing their behavior and trying to understand. It wasn't.
I say that's what a lot of research right now about large language models is there's a model and then people are doing psychology on the model.
All right, so I'm porting it into robotics. So we will bring our robots to this rink and kind of like have some tests. I think that is connecting to what we were discussing before. I think this functional testing or behavioral testing is a good way. It's even a good way to just say we're not advocating for a specific solution. We're advocating for a specific capability or a specific behavior, or some guarantees in these conditions. This is the amount of failure that you admit. But of course, it's going to depend on the task. If it's about loading my dishwasher, maybe I don't care so much. If it's about, I don't know, feeding my 3-year-old, it's going to be also a much higher bar for failure. So it depends on what is the task. But I think I advocate for a behavioral approach of evaluating how well do we do in a task. And that to me is kind of like the standard way.
Yeah, maybe just to reiterate that, I guess I would say, like, when I go and get my driver's license, right, I take a test. Somebody in the DMV tells me, yep, David, I guess you're competent to drive on the road. My grandma is, she's still got her license, but at some point, maybe they'll tell her, sorry, you're not allowed to drive anymore, right? So there's tests, and these tests are behavioral. They apply them for pilots. They apply them for everything else. So I think if we don't have the ability to reason at any more granular level, then I think that's the best we can do.
Yeah, and I would just say, like Roberto said, it definitely depends on the application. For an entertainment robot, mistakes are cute, right? And so you don't need a lot of reliability. But there are definitely applications where you need those many nines of reliability. I guess I hinted at this earlier, but I'm always trying to advocate that we have too high a standard for perfection in robots. That especially in tasks where people make mistakes, we should be quicker to deploy and then learn from the mistakes and sort of have them improve over time. Autonomous cars is my favorite example of this because people there's 40,000 fatal accidents a year in the U.S. Because of human with human drivers, and yet we're requiring that there's no accidents with autonomous drivers before we get them out there. And to me, that seems like too high a standard. I mean, there's an opportunity cost. So let's. I know Rod, you had your hand up. So now we can learn what we said that you disagree with.
No, I don't disagree at all. In the past, some academics have done inventions in academia, which have had enormous impacts later. And I think about the bitmap display, which had to be invented. RAID discs, that was Randy Katz at Berkeley. These were things that then went on to change the world. And they weren't done in industrial labs. They happened to be. You're talking about general purpose robots. You seem to be talking about them in the home. If I look at the world from a point of need, elder care is just a tsunami coming. We see the birth rates in Japan, Korea, Italy, and the US, Spain. What about, to me, if we could do some things which help the elderly stay in their homes longer with independence and dignity, that is going to be a good thing for us. And I've got an interest in this. So how do you've been talking very technically about safety, this, that, learning. What about invention in domains where there is something crying out in the world? Until there are good ideas, nothing's going to happen. Why don't you guys invent better elder care robots?
You want to answer this?
You got it.
Well, I don't know. I'm on it. I have to say, in my last grant proposal, I argued that it would be great to have robots helping for that reason. And one of the reviewers said, I don't buy it until someone demonstrates that the robots are helpful for elderly care. It's just a claim. And like, okay. But yeah, I believe also it can help. And yeah, as you mentioned, it is actually a need, and we're seeing it coming. I think Japan has been kind of like trying very hard on that direction. I think some of the things in terms of safety, they are very interesting. If you search for Japanese robot caregivers, they are very interesting embodiments they are trying, soft robots that go into the safety side of things. So I'm more on the computational side of things. I explore some embodiments, but I'm also on the computational side of things, not super tailored for elderly care, but tailored for safety, which I think is general for elderly care or other home applications. So yeah, I think inventions will come. But yeah, I still think that there is the components of safety that we were discussing before. I think there is an additional component, I think, in this specific application, which is company and kind of like entertainment. Because if it's a home robot that is kind of like helping a family to kind of like clean the house, it may be okay that it's kind of like just doing its job. But if we really want and we need to kind of like complement help from humans on elderly care, one thing that we need to take into account is how to not replace human touch that people are still, at least if they have a robot, they still have someone to converse with, which I think LLMs have been great on creating that, because I think there is not just the manipulation aspect of it and not just the practical aspect of it, but if we're unfortunately not going to have help from one human per elderly house that we want to get autonomous, we don't want them to be isolated from any kind of like interaction. And if we can compensate with some lack of interaction with humans with interaction with an agent, that at least kind of like keeps you alive and kind of like entertain. I think that is an important aspect for that specific application beyond just manipulation.
Yeah, I would say, I mean, I agree that elder care is a fantastic domain. In fact, I sort of have the sense that's, for me, through my career, is the one that I've seen everybody talking about and for many, many years, but still never any product. The first time I remember seeing, and it probably people were talking about it well before, but when I was still a PhD student, so 30 years ago or something, Martha Pollack was talking about elder care as the grand challenge for robotics, and then she, of course, went on. She was recently the president of Cornell, so she moved on up into administration, but she made the case, and I think there's fantastic aspects about it from a product perspective. Is that you can get in with aspects of just being a companion, or reminding you to take your medicine, or notifying your kids if you've fallen or you're not moving or something like that. And then there's all kinds of opportunities that are much more difficult, where you would have to move mass, to help somebody out of bed, or help them get their clothes on, or these kinds of things. But you can be useful without that much capability, and so it is one that I've been sort of surprised that there hasn't been more, sort of starting small and having that elder care from a product perspective. And then I think a fantastic point about just caregiving in general. And so I was a part of the 100-year study on AI, and I've been a leader in that. And in the 2021 study, there was a section that was motivated by a workshop that we called Coding and Caring. And there's a nice, sort of 4 or 5 page blurb about many of the issues that come up if we're going to inject AI in general and robotics in addition into care. And I think there's tons of opportunities, but also we don't want to replace the human caregiver. It's a very personal and intimate kind of thing, and so it'd be sort of dystopian if we got to the point where people were replacing all human contact with the ability to interact with robots. So we do need to proceed with caution, or when doing this. But I think there's all kinds of opportunities. Yeah. Here. Go ahead.
Yeah, the other thing, to follow up on the great question from before as well, for elder care, my great aunt was 102. She always wanted somebody to help her make tea. It could have taken an hour. She wouldn't have cared. You could have failed 100 times as long as it didn't break the pot, right? As long as it could keep trying, that's fine. And then to just a note there, but the question I had is, how far for general purpose applications like that, like making tea or preparing a plate of mixed fruit, again, for my great aunt, how far do you discretize a task down into primitives or bite-sized pieces before it gets too far or becomes unwieldy? Because I can imagine, you could break down, cut an apple into disassemble this spherical food, and keep going and going and going until you have a useless mass of hundreds of tasks to do something simple. So how do you guys approach this?
I don't think there is a good answer for that. I think it's an exploratory process. Whatever works, works. So how granular should your primitives be? I think if you go very granular, it becomes easier for control, but then planning becomes much harder, because then each of your plans are going to be hundreds of tiny, tiny steps. If you go to the extreme of being very, very coarse on your symbols, one entire symbol could be solving the task that you're looking for, so then it's easier for planning, but then you're doing everything on the control side. So I think there is somewhere in between predictability about the abstractions that you are creating in order to reason about what is the best path to achieve that, while still keeping those symbols kind of robust and kind of like a well-defined and easy to control. Yeah, I mean, the field is kind of like moving in different directions, and I think even now the latest foundation models, they are also kind of like exploring with these two-level paradigms, where the highest level is kind of like dictating small steps in language to a lower level that is language conditioned. So there is clearly something to gain there, because you cannot kind of like flatly reason about a very long task. What the best abstraction is, I think it depends on these factors, on predictability of your symbols, reusability of your symbols, and controllability of how you implement that with a robot in a kind of like, robust way that has always the same outcome. These would be kind of like the general rules, but I don't have a one answer to what are the perfect skills to learn for a robot.
Maybe just to echo a little bit of that, I think this is, like, you've hit on a very important and long-standing challenge, right? And it's not just in robotics. Like, I'm pretty sure this may be from one of Richard Murray's textbooks in control theory, but I've heard this called like an artful decision that you have to make anytime you design a model predictive controller, as an example. But basically, you always have to make these decisions of like, okay, what is the high level? What do I call high level? What do I call low level? What do I call next lowest level? Where do I draw these lines? What timescales do all these things operate at? What latencies can I tolerate? All these things. And people have been working on this for upwards of 30, 40 years. And here we are. So I mean, it's a hard problem. I don't really have much more intelligent to say about that, but.
So I think we're, I'm starting to hear stomachs rumble with hunger, or maybe that's just mine, I don't know. But so maybe to close, we'll take one more question. There's somebody here, and then I'll give each of you an opportunity to leave the audience with your best words of wisdom, and then we'll go to lunch, so please.
So beyond academia, are you guys aware of any research or innovations or inventions indeed coming from industry that are surpassing what's going on in academia?
Oh, yeah. I mean, there are several areas. I think there is a very nice competition. So it's starting from embodiments. I mean, we kind of like try things out, but I think to kind of like make them kind of like better, there is an industrial process behind, and I think we have seen kind of like this Cambrian explosion of different embodiments right now, humanoids, non-humanoids, whatever. So that is something that is on the industrial side. When it comes to more CS-like, I think there's a bunch of kind of like startups right now that are trying very interesting things, and they're pushing the boundaries in ways that are going beyond what academia has done. I would say those startups are basically academics that go into industry for a little bit. So it's very much driven even kind of like output paper. So it's kind of like some form of, different, but very interconnected. But definitely there is very good research going on right now that is trying pushing the boundaries of what is possible with robot learning for manipulation, for mobile manipulation, and for generalist robots. So definitely, yes, there is a very healthy competition right now between academia and industry.
Yeah. I mean, as far as where is industry outpacing academia, if we're talking about AI, just go to like Claude.ai, something like that. But I think in robotics, we're in this very happy middle ground where, as far as I can see, basically academia is at the frontier, but also industry labs like NVIDIA Robotics as an example, or Amazon Robotics, other industry R&D labs that collaborate with academia. I think those are like great examples of how where industry is pushing the frontier. Sometimes it's with academia, sometimes it's not. But I think in robotics as a field, we haven't. Everybody is still relevant.
I mean, I sort of object to the question. So like, what do we mean by, you say, is it better, is stuff's better happening in industry versus academia? From my perspective, it's different, but better for what? And I would also say I wouldn't frame it as competition between industry and academia. I think it's synergistic. I think there's a lot that I do different things in academia than I would do in industry. And, you know, the role in academia, in some sense, you know, the role in industry is to take all of the technologies that are there and say, what product can we build that will have a market, that will have customers within a relatively short time period in the next 2 to 3 years or so. And the role in academia is to say, let's think 10 years in the future and unlock the next the next possibilities. And also, by the way, let's train the people who are going to be, you know, starting and moving into the industrial realm. So I think, you know, it's a healthy interplay between them. You know, we use commercial products in academia, but then try to, you know, go push them beyond what they're being used for in industry. So I think it's a fantastic time right now where there's a lot of exciting things happening in industry, but also you know, that wouldn't be happening if we didn't have the sort of the rich support of the people, the technology, the ideas that are continually coming out of academia. So, so let's. I know it is lunchtime, so let me just, if either of you has a wrap-up comment you want to leave, your words of wisdom for everybody on general-purpose robots and where we're going. No pressure.
I don't know. I'm hungry.
Yeah, I think there's a lot of opportunities. I think there is definitely also something to gain by trying to create agents that are good at several things instead of being kind of like very narrow. And I think there is some opportunity on how can you squeeze out of learning something or being able to do something, how that helps in other things. So I think that is one of the powers of generalist robots, and that we should tap more on. By making them having to be general, then it becomes easier to be a specialist on one specific thing. I think that is where we're trying to get to. I don't think we're there yet, but I think that is the opportunity with generalist robots.
All right. Great. So thank you for bringing us in. Thanks all of you for your attention, for your questions. To me, I think this has been a fantastic morning. Great talks, great discussions. And now we encourage you all to go get some lunch and mingle and you know, share your thoughts of what's happened this morning, and then come back at 1:30, I believe, for an exciting talk from Chao Yi of Booster Robotics.